Okay, 8.1, we're exploring the logarithmic function. So we've looked at this before. We're investigating the inverse of exponential functions. So before we looked at the inverse earlier in this textbook, we saw for a linear function, we saw an inverse look like that. And we focused more on the quadratic function or exponential function, where the inverse looked like this. And it was actually a reflection across the line of y equals x. Okay, so we have that line. And that's what we noticed. So right on y equals x, that's where those 2 points would touch. Okay, and what we're going to find out is for logarithmic functions, the pattern is the same as for exponential functions. So we get this sort of reflection happening across y equals x. We're gonna show that in a minute. So here's the inverse of a linear function such as 2x plus 1. We get also a linear function. The inverse of a quadratic function such as g at x equals x squared has a shape that is congruent to the shape of the original function, and it's reflected across y equals x. All right. So what does the graph of the inverse of an exponential function look like? Y equals 2x. Who remembers that parent function? Anybody know what this graph looks like? Yeah, the back, Joseph.
It's always going upwards?
Yeah, right. It's always going upwards. It crosses through 0, 1. It looks like this. Okay, so what we want to do then today is discover what the inverse of this function looks like. Okay, so as I mentioned, it is going to reflect across the y equals x line. So we're going to get something like this. Okay, but we're going to show that in a minute. So it says consider the function 2x. Create a table of values using integer values for the domain -3 to 4. Okay, so we can just build a table. Our x values. So there's our table of values here on the left. So -3. And we just plug in those values of x to the exponent of 2x. Can everybody see that?
Yeah.
And we create this table of values. Okay? So there's our graph, which again I drew just roughly. And it says, on graph paper, graph the exponential function in part A. State the domain and range. So the domain of range of this function then is pretty easy. The domain is what? Yeah, Marco? XER, right? Because we're covering all x values. And the range, yeah?
YER where y is greater than 0.
Yeah, y is greater than 0. And you can see that down there. But we can see that the y values are just above 0. Okay, so the next step it says interchange, see here, interchange x and y in the equation for h to obtain the equation of the inverse relation. State a table of values for the inverse relation. How does each y value of this relation relate to the base 2 and its corresponding x value? So just like we did earlier in this textbook, when we do the inverse, we just change these values. Okay, so where these values were before, okay, those values are just going to switch spots, and what was your y values becomes your x values, and your x values become your y values. So these would switch over. Etc. Okay, so that chart looks like this. Any questions up to there? That's the first step. We just switch x and y. So that's the graph or the table of values for our inverse function. If we go then and graph that, we get the lighter colored graph. A little difficult to see here, but it's right here across the reflection of y equals x. Okay, in light gray here. Any questions there?
What's that?
So this is the inverse function. This is the once we switch the x and y values, so we obtain this table of values here. Nailed? Now graphing that out, so 0.0253, that's this graph right here. Do you see that? Okay, so now we see that the inverse of an exponential function is reflected across the axis of y equals x. Okay, so far up till now, just basically it's been a review. So the inverse is a function since for each value of x there's only one corresponding value of y, so it's definitely still a function if we were to do the vertical line test. The graphs of the inverse function of y equals 2x and x equals 2y are symmetrical about the graph of y equals x. So that's what I was talking about, the reflection across the y equals x line. Okay, this is important to note here. So see how this equation here, y equals 2x, there's our original exponential function. Our inverse function, we just switched the y and the x. So x equals 2y. Another way of writing this, and this is where kind of the new logarithm idea comes in, is this. So these two equations here are the same. Okay? X equals 2y is the same as saying y equals log 2x. Okay? And you might ask why? It's by definition. Okay? It's because that's the way they've defined log. Okay? So this is what they're saying. They're saying the value of y, log 2x, is equal to the exponent you need to raise 2 to get the value of x. Now that was a lot I said there. I'm going to say it one more time. Okay? This value, y, so log 2x, it's equal to the exponent that I need to put to 2, so the exponent I need to raise 2 to get the value of x. Any questions there? Okay, so if we had something like this, okay, what is the value of y? See who gets it first. See who's understanding it. What's the value of y? Don't use your calculator. No, because this is the point.
Is it in squared?
No. I'll say it one more time and then you guys can guess. Okay, one more time. The value of y is the exponent that the base, 2, needs to be raised to get the value of x, which is 8. So what's the value of y, Gianluca? 3, yes. Okay? And again, you might ask why? Well, why is that the case? It's by definition. That's how they're defining log. Okay? Why? Well, we don't know why yet. They're doing it because this is one way we can represent many different graphs, okay, in real world application. But that's the reason. So, let's try one more. Yeah. Okay. So y would be 2. So now if we were to graph, if you can imagine graphing this then, what would be the point here? What would be this point? What would be one point on this graph? Because it is a function, right? What would be one point? Gianluca. Very good. Yeah, excellent. See, he took the x value 8 and he took the y value 3. So one point would be 8, 3, somewhere over here. Okay? What would be a point on this graph? Alex.
25, 2.
Very good. 25 and the y value 2. Excellent. Okay, good. So that already now you guys have a conceptual understanding of what logarithms are. So if someone were to show you something like this, you could say, okay, well, I know that's going to be whatever 2 has to be raised to give me 8. This is 3. Okay? And these numbers can change, right? Both these numbers and these numbers. This is called the base, and this is the x value. The base by default, so just like when we take the square root, you know how we have the square root? This number is a 2 here. By default, it's the square root. The base default on any textbook or on your calculator is actually 10. Okay? So if you just see this, what's the value of this? Right, 2. Good. Because the base here is 10. If it's not seen, it's 10. Okay? So what does 10 have to be raised to get 100? 2. Okay.
So, sir, how do you put in a different value there instead of the 10?
Sorry? Oh, your calculator will have a button that looks like this. Log x, okay? Just like you have this button, right? Or whatever it is for the square root. Okay, D. All right. Where are we? On the same axis that you use to graph the exponential function in part B, graph the inverse. Is the inverse a function explained? So the way we graph the inverse again is we created the table of values by just switching the points, and then we just graphed it. Okay, and we got this graph here. It is a function because the vertical line test passed. Graph the line y equals x on the same axis. How do the graphs of the exponential function 2x and the graph of the logarithmic function h to the negative 1x equals log 2x relate to this line? So how do they relate? How does this and this relate to this line? Marco? Yeah, it's a reflection. Good, we've been talking about that. F. Repeat parts A to E, first using j at x equals 10 to the exponent of x, and then using k at x equals 1/2 to the exponent of x. So we're going to repeat them by creating the table of values. So that's this part here. So x this time is negative 3, so this value here would be 10 raised to the exponent of negative 3. Okay, so we just create these table of values. So there's one. This is for y equals 10x. And then this table of values is now the reciprocal of that. Okay. Sorry, not the reciprocal, the inverse. So we switch the x and y values. Again, the same process, right? And now we're doing it for 1/2, and we switch the values again, and now we graph. So here's the graph of y equals 10 to the exponent of x. What's the difference? Does anybody notice? So the base now is 10 instead of 2. Nicholas, what's the difference between this graph and the one we looked at earlier?
Sorry.
Okay, so the graph we looked at earlier was very similar to this, right? Here, I'll go back. There. So there's the graph. This is y equals 2 to the exponent of x, okay? This graph over here is y is equal to 10 to the exponent of x. Okay, what's the difference? Yeah, exactly. So just like how we see with stretches, right? In vertical stretches and compressions, as that value gets bigger, as that a value gets bigger, we get this sort of vertical stretch happening. Okay, so it gets closer to the axes, to the y-axis here for the exponential function, and for the logarithmic function, it gets closer to the x-axis. Okay? So if we imagine what's going to happen with 1/2, it actually gets further away from the y, further away from the x. Okay, so we get that sort of vertical stretch happening as that base value gets bigger. Okay? State the domain and range of the inverses h, j, and k. So, if we look at this graph, who can tell me the domain of the dark, the exponential function? What is the domain? Anthony? The domain of this, so it goes like this. X cannot equal 1. No, it definitely passes through 1, yeah. This is important, guys. You gotta at least have the basis for domain and range, right? Doesn't go away. I'm gonna help you out, yeah.
Yeah, XER.
Yeah, XER, right? Because although this looks like it's kind of, because it's so steep, it almost looks like it's going to vertical asymptote. It's not. Okay, it's going on forever in the x direction. Okay, and Daniel, what's the range? Actually, sorry, before you do that, let's talk about, so that's the domain for the black line. What is the range for the lighter line? The range for the inverse?
It's all
Alex.
all of the numbers.
Yeah, so it's YER, right? So notice this, the domain for the exponential function is XER. The range for the inverse function is YER. Okay, so that pattern is going to persist. So what's the range now for the exponential function? Jason, so the dark line, what's the range?
Can't equal 0.
No. You're right, it can equal 0, but you need to be more specific. The range.
All real numbers.
Sorry?
All real numbers, y can't equal 0.
No. You're close. I think you would have it if you're right. Yeah.
Y has to be greater than 0?
Yeah, it has to be greater than 0. Okay? That's what you meant, right?
Yeah.
Yeah. So it has to be greater than 0. So that's the range for the exponential function. Kevin, what is the domain for the inverse function?
X is all real numbers, X cannot or is greater than 0.
Yes. So you see that? The range for this was y has to be greater than 0. The domain for the inverse was x had to be greater than 0. So the range, the domain and the range are switched. Okay, we're going to see if that pattern persists. So here's this one now. We're looking at the black line here. Naod, what is the domain for the black line?
Domain XER.
Yes, XER. What is the range for the light line, Naod? So the gray line, what is the range?
The range YER.
Yes. Okay, so see how the domain for one is the same as the range for the other. Let's try one more. Kevin Trin here. What's the range for the black line?
Black one, the range.
Yeah.
All right. Y is an element of all real numbers, and y is greater than 0.
Good. And what is the domain for the light one?
Same thing. X is all real numbers. X is greater than 0.
Perfect. Okay, so that's the pattern that we're trying to establish. And it works out. Okay, how is the range of each logarithmic function related to the domain of its corresponding exponential function? We just answered that, right? Luke? How is the range of each logarithmic function related to the
they just
domain?
swap.
Sorry?
They swap.
Yeah, they're the same though.
Yeah.
They're the same, yeah. How is the domain of the logarithmic function related to the range of the corresponding exponential function? Same thing. They're the same, right? They just switch x and y values. How would you describe these logarithmic functions? Create a summary table and include information about intercepts, asymptotes, and shapes of graphs. Okay, so let's figure that one out. We'll look at these two graphs here. So for the exponential function, so the dark function, Joseph in the back, what are the asymptotes?
Dark function?
Yeah,
X 0.
yeah. Xy is equal to 0, right? Yes.
X is equal to.
No, there's not one there. It looks like it, but there's not, okay? This keeps going. Even though it keeps going at a really steep rate, there's no vertical asymptote, okay? What is the asymptotes for this dark line here? Elijah. Asymptotes for the dark line. Right. So for the dark line, for all exponential functions, there's a horizontal asymptote at y equals 0. Okay? With that, when there hasn't been any translations, okay, there's a horizontal asymptote at y equals 0. Okay? For the light line now, Alan in the back, what's the asymptotes for the gray, the inverse function?
X is equal to 0.
Right. And you see how it's the same? Do you see that? So we can say conclusively then that for all exponential functions, there's a horizontal asymptote at y equals 0. And for all inverse functions or logarithmic functions, there's a vertical asymptote at x equals 0. Okay? So that's one conclusion. The other conclusion we'll note is about the intercepts. Okay? Who can tell me? There's both graphs. You can see both axes there. All the intercepts. Who can tell me what they notice about the intercepts? Jesse.
Like the x-intercepts are where the y-intercepts are. Like, so, like, if the intersects at y equals 1, there's an intersection at x equals 1 for the logarithmic function.
Yes. So in other words, just, saying straight, the exponential function intercepts the y-axis at 1. Logarithmic functions intercepts the x-axis at 1. Okay? You guys see that? Intercepting at 1, intercepting at 1, intercepting at 1, intercepting at 1. So if you're drawing these and you draw a logarithmic function and there's no translations, it has to go through 1 on the x-axis. That point will always be there. Okay, just like that point is still there. See? Any questions there? Okay. Next question. What point is common to the graphs of all these logarithmic functions? We just talked about it. 1, 0. Sorry? How are the graphs of an exponential function and a logarithmic function with the same base related? They have that reflection happening across y-axis. How are the graphs of h at x equals 2 to the exponent of x and the inverse related? How are the graphs of the logarithmic functions related? So the graph we're considering is this graph here. That's to a half. And this graph here, which is to 2. This is L. So the graph of y equals 1/2 to the exponent of x is the result of reflecting the graph of y equals 2 to the exponent of x about the y-axis. So there's a reflection across the y-axis when we have the inverse base, or sorry, the reciprocal base. The graph of h at x and k at x are mirror images in the x-axis. So if we look at this original graph in black, this is y equals 2 to the exponent of x. If we reflect that across the y, so it looks like that, we should get the graph of y equals 1/2 x, which is there. Okay? So when we have the reciprocal base, it's a reflection across the y on the exponential graph. On the logarithmic graph, it's a reflection across the x-axis. So here's our logarithmic original function. We're going to reflect that across the x value. So this is going to go up and that's going to go down in the 1/2. And that's what happens here. Okay? So when you flip the base, you reflect across the y and the x-axis accordingly. Okay? Next question. How does the value of a and y equals a to the exponent x influence the graph of log a to the exponent, or sorry, logarithm of base a x? How might you have predicted this? Anybody? How does the value of a influence this graph? We talked about it earlier. The value of a, Alex.
The value of a is higher, it's closer to the axis.
Perfect. Yeah. As the value of a is higher, those lines going to infinity approach the axes. The graph of that includes the point 8,3. Therefore, 3 equals log 2, 8. What is the value of log 2, 16? So everyone, I hope, knows this now. What is this? Okay, without yelling it out, who can tell me just with their hands up the value of 2 to get an idea of who knows what it is? No, Philip?
4.
2 to raise to the exponent of 4. Very good. 16. Excellent. Okay? So 2 raised to the exponent of 4 is 16. Any questions about that? That's the definition of logarithms and how they work, okay? So if you understand that, just looking at that, that's great. All right. In summary, the inverse of an exponential function is also a function. It can be written as x equals a to the exponent of y. This is the exponential form of the inverse. An equivalent form of x to the equals a to the exponent of y is y equals log to the base a x. This is the logarithm form of the inverse and is read as the logarithm of x to the base a. That's how you would read it. The log of x to the base a. The function y equals log ax is called the logarithmic function. Since x equals ay and y equals log x to the base of a are equivalent, a logarithm is an exponent. The expression log ax means the exponent that must be applied to base a to get the value of x. For example, log 2/8 is equal to 3, since 2 to the exponent of 3 is 8. Okay, I hope everyone gets that now. The general shape of the graph of the logarithmic function depends on the value of the base. When a is greater than 1, the exponential function is increasing. So we get this pattern happening, and we cross through 1, 0. We get this pattern for the inverse happening when a is greater than 1. And we cross through 1, 0. 0, 1, 1, 0. When a is a fraction, we get the opposite happening. We get a reflection of the y, right, of the whole number. And then we get the same pattern of reflection across y equals x. Remember, when you're reflecting across y equals x and your graph crosses over, the reflection will cross over that same point on the y equals x, right? Because if you're going to flip something on that actual, that'll be your pivot point, right? Although this doesn't look like it, this dark line here, it is a reflection across this y equals x. Because if you can see, if you took this part of the dark line and flipped it across, it would come up here. This part, if you flipped it, would come there, okay? So it's not as easy to see as this one, but you can actually see it's still a reflection across the y equals x line. The y-axis is the vertical asymptote for the logarithmic function. The x-axis is the horizontal asymptote for the exponential function. So we talked about that. There's an asymptote here and an asymptote here. Here for the exponential, here for the inverse. The x-intercept of the logarithmic function is 1. The y-intercept of the exponential function is also 1. We talked about that. The domain of the logarithmic function, xer, since the range of the exponential function is yer. So your domain and range is flipped. Okay, any questions?